Good afternoon, everyone. Thank you for coming to UKSPA seminar again. And today we have Nicolas Papernot to give us a talk on differential privacy. Nicolas is an assistant professor in the Department of Electronical and Computer Engineering and the Department of Computer Science at the University of Toronto. He is also a faculty member at the Vector Institute, where he holds Canada CIFAR AI chair, and also a faculty affiliate at the Schwartz-Reisman Institute. His research interests span the security and the privacy of machine learning. If you work in this area, you definitely have heard him before. Nicolas was recently named a Sloan Research Fellow. He also received a Concord Researcher Award and was previously a Google PhD Fellow. His work on differentially private machine learning received a Best Paper Award at ICLR 2017. He is an Associate Chair of IEEE Security and Privacy Conference, the Auckland Conference, and an Area Chair of NeurIPS Conference. He earned his PhD at Penn State, working with Professor Patrick McDaniel. Upon graduating, he spent a year as a research scientist at Google Brain, where he still spends some of his time. Today, his talk is differential privacy a silver bullet for machine learning? Now the stage is yours, Nicolas.
Thank you, Cheng, for the kind introduction. And also thank you for inviting me. I'm very excited to give the talk today. I hope this will be one of the last virtual talks for a while, but we'll see how that goes. I also hope we can make the talk interactive. So as we mentioned earlier, feel free to stop me if you have questions. I'll try to monitor the chat myself as well. Also, before I started, I wanted to mention that this is going to be a presentation about work that I've done in collaboration with a lot of colleagues at the different places that I've been at in the last couple of years. And also recently, a lot of work is in collaboration with my students here at the University of Toronto. So I tried to put the title of the paper and the name of the authors at the bottom of the slide so that you can sort of reverse engineer who contributed to each project that I'm going to be describing today. So the idea overall is to give an overview of the work that we've done on privacy in general. It was sort of this leading question of, is differential privacy a silver bullet for machine learning? When you see a talk like this with a title like this, you can imagine that the answer is going to be no, but I'll give a little bit more details and try to argue in favor and against differential privacy, and you'll see that the answer to the question is not as simple as a yes or no. Okay, so to get started, I wanted to sort of introduce the background by stating what the definition of differential privacy is. And I'd like to say that it is a very difficult notion to basically characterize privacy in general, because it's very subjective. If you ask different people what they think privacy means, you'll very likely get very different responses. And so I think it's quite remarkable that differential privacy has generated so much consensus in the research community around a single definition of what it means for an algorithm to be privacy preserving. And so here, this is an overview first of the intuition of what it means to be differentially private. The algorithm is essentially given two different data sets here. The first data set at the top contains the record for one individual here, whereas the second data set at the bottom does not contain that record for that same individual. Otherwise, the two data sets are completely indistinguishable. They're in the same pieces of data. Once we pass these data sets to the randomized algorithm, what differential privacy requires is that the outputs that the algorithm is making are indistinguishable to an observer that is essentially monitoring the outputs of the algorithm. And so what that means to be indistinguishable Sorry, I'm not sure why my video is. Hopefully this fixes the video. So what it means to be indistinguishable is essentially that the adversary is not able to infer whether the algorithm was operating on the first data set or the second data set here at the bottom. Okay, and so of course, if the guarantee was not probabilistic, this would mean that the algorithm is not able to extract anything from the training data here, our data set. So instead, we're going to look at the probabilities that the algorithm makes certain output. And in practice, we're going to require the following. We're going to look at the probability that the algorithm M makes specific output on the first version of the data, which is D. Look at the probability that that same algorithm M on another version of the data, D prime, makes the same output here, S. And we're going to compare these two probabilities. And you can see here that there is a parameter epsilon. The smaller this value epsilon is, the closer these two probabilities have to be, because essentially we're requiring that this relationship holds here for all possible pairs of D and D prime that only differ by one record. Okay, and so you have to think about it the two ways that the inequality needs to hold. And so you're defining an interval, and you're saying the smaller value of epsilon is, the closer the probability that the algorithm makes certain output is, regardless of whether I included or not that particular piece of training data. And so what that means is that the smaller the value of epsilon is, the less the adversary is able to tell whether we're operating in this first setting or the second setting. And so the more privacy preserving the algorithm is, in fact, you would even not be able to tell whether or not this person contributed their data in the first place. And so having stated this definition, the question is, how do we obtain machine learning algorithms that provide this guarantee? Okay, and so there are multiple approaches. One that I'm not going to discuss today is essentially modifying stochastic gradient descent and requiring that essentially each of the gradients that are computed by gradient descent are clipped and noised. Instead, I'm going to introduce a different approach, which we worked on in the past, and which has the advantage of being very intuitive. So it allows to build some intuition for why privacy is aligned with the question of generalization in machine learning and how we can obtain this notion of differential privacy. So the idea is here to start with the set of data that we want to learn from. So this is our private data set. And we're going to partition this private data set in multiple subsets of data, here from 1 to n, with the only requirement that there is no overlap between these different subsets of data. So there are partitions in the mathematical sense. Once we have these n subsets of data, we're going to train independently a model on each of these subsets. And so we'll call these models teachers, and you'll understand soon why. But there is no requirement as to how we train these teachers. They don't have to follow any specific algorithm. It could be a decision tree, it could be a neural network, in stochastic gradient descent or not. It really doesn't matter, as long as we have a model that essentially learns from this set of data here. And so the question then is, how do we have this ensemble of teacher models? They all perform the same task, but they all independently learn from one another. How do we have them predict in a way that's privacy preserving? The next thing that we might want to do is say, well, I'm going to just aggregate the prediction of these teachers. So I'm giving them a test example. I look at the labels that the teachers predict, and then I output the label that received the most number of votes. And you can see how that puts some form of privacy in the sense that if all the teachers agree on the same prediction, then it means that the prediction does not depend on a single piece of data here, a single subset of data here. And so it does not depend on a single piece of data in your original training set. However, there are corner cases where, for instance, if you have half the teachers voting for one label, half the teachers voting for another label, then essentially one teacher can change the label and then change the output of the aggregation, which is problematic in terms of privacy. And so this is here why you see noisy aggregation, because what we're going to do is we're going to build this histogram of votes
and perturb the histogram with some random noise. And then only we take the label that received the most number of noisy votes. And that allows us to obtain this notion of indistinguishability that I described here, where you can see that we now have a probabilistic randomized algorithm. And so we can essentially show that this noisy aggregation mechanism provides differential privacy guarantees. In some sense, you can think of this whole setup here on the left as a differentially private API that you query and you receive a label that is guaranteed to come with differential privacy guarantees. The problem is that the more you query this, this ensemble of teachers, the more you expose the data that was used here, because while each query comes with a differential privacy guarantee, the guarantee does not prevent all leakage. It bounds how much leakage is happening. And so each query comes with a small amount of risk that we're leaking private information. And so what we're going to do is we're going to have to limit and fix the number of queries that we're making to the noisy aggregation. Okay, so the way we do this is we have this knowledge transfer step where we assume access to unlabeled public data. And then we use the unlabeled public data to query the ensemble of teachers. The ensemble of teachers is going to respond with the noisy label, which is then used to train a student model, which will be used to answer eventually the user queries. The benefit of doing this is that once the student model is trained, the cost in terms of privacy is fixed because we no longer need to make queries to the ensemble of teachers. We can even delete this ensemble of teachers altogether. And so you can think of this as doing privacy preserving knowledge transfer from an ensemble here of teachers into the student. Okay. And what I like about Pate here is that it shows very well why privacy, and in particular differential privacy, is aligned with generalization, which is the goal of machine learning algorithms. And in particular, you can see that in the consensus that you can observe among the teachers. So here, if most of the teachers agree on the label that they vote for, then this means that there is some notion of generalization in the sense that they all independently came up with the same prediction using different pieces of data. And so you can see why this means the prediction is more likely to be correct. On the other hand, if there is this strong level of consensus, what that also means is that you can answer requests label this point with much stronger privacy guarantees, because the amount of noise that you can add in the aggregation step is larger before you start changing the label that receives the most number of votes. And so what that means is that you can prove stronger differential privacy guarantees when there is more consensus among the teachers. And so these things, these two observations show why there's this strong alignment between differential privacy and generalization. In fact, differential privacy is a worst case notion that implies sort of generalization, which is an average case notion. And so why that is interesting, first of all, conceptually speaking, but also practically speaking, because this allows us to simultaneously improve the utility and the privacy of Pate by ensuring that there is a minimum level of consensus among the teachers before we reveal their prediction. And so this is in fact what we propose in this paper, where we said, well, let's, rather than answer all queries that we're being asked to label, let's first select the queries for which we have high consensus. And then if we don't have high consensus, then we don't respond, okay? And then we split basically the privacy budget we spend between selecting queries and answering queries. And what these graphs are showing you is that essentially by having this consensus check, we were able to not only answer more queries, because each query comes at a smaller privacy cost and is more likely to be correct. So we simultaneously increase the accuracy of the predictions we're making, but also the privacy that we're achieving. And this is very, very unusual. And I wanted to show it sort of as a first win for differential privacy. This is where you can see that when things work well, we have this very nice line of properties that are very desirable in machine learning pipelines. So in case there are any questions, this is a good point to ask a first question. Otherwise, I'll continue with the presentation.
Okay, I want to ask a question about when you have multiple teacher models, do you have any assumptions on how the data is distributed when training the teacher models?
Yeah, that's a very good question. So essentially here, our only requirement is that there is no overlap between the subsets of data that each teacher is receiving. And that said, the way that we created these partitions is simply by uniformly sampling from the original data set. But I'll cover later in the presentation the case where these partitions organically existed in the data set. And I'll probably give a better answer to that question at that point.
Okay, thank you.
Yeah, thanks for the question. So while there is this strong alignment between differential privacy and generalization, in practice, there is still some overhead associated with learning with differential privacy. And we observe very often tension in the sense that the more privacy we provide, the lower the utility is, in particular when compared to a non-private model. One way to mitigate this is to realize that, and this is here on the left, that we can design architectures that are more amenable to learning with privacy guarantees. And so here you can understand this in the sense that when we learn with privacy, we don't want to learn too much from each training point. And so what we observe in this paper is that the default choice of activation function, which is the ReLU activation function in the neural network, is not optimal for that purpose because it's unbounded. And so the activations can take arbitrarily large values, and this allows the training points to have more impact than we would want to preserve their privacy. Instead, if we use 10H or other tempered sigmoid activation functions, then they are bounded. And so that makes it easier to train these architectures with differential privacy. And this is what you can see here, where if you compare for each of these three data sets, the non-private baseline with in bold the privacy preserving result we achieved, we actually closed some of the gap between previous results that achieved differential privacy and the non-private baseline. So this shows that we shouldn't just take a pipeline that works without privacy and then expect that if we repeat the training with a differentially private optimizer, then this pipeline is going to give us the best privacy utility trade-off. Instead, we should design the pipeline with the fact that we're going to train differential privacy in mind. Okay, so that's the first result. That said, as you can see, these results are still not exactly matching the non-private baselines. And so what we try to understand here on the right is whether this is due to the fact that the privacy analysis is not sufficiently tight and could be improved to basically show that we are getting stronger guarantees than what we think we are getting, or whether this is something more fundamental and we just have to find new, different algorithms for learning with privacy. And so here we looked at a common approach for learning with differential privacy, which is differentially private stochastic gradient descent, which I briefly alluded to earlier. And you can see that what we're trying to do here is compare the red dotted line, which is what the analysis tells us is how much private information may leak in the worst case, with what a concrete adversary can actually infer about the training set, and how much private information the adversary is effectively able to extract when mounting a concrete attack. And what we see from the left to the right is that the more theoretical the adversary becomes, the closer it gets from this worst case the analysis is telling us is possible. But if you take it the other way around, the more practical the adversary becomes, the less in practice they are able to leak in terms of private information. And so what that means here is that if you compare the analysis to the practical adversary here, then the practical adversary is not able to extract nearly as much information as what we would have assumed when performing our analysis. And so what that means is that we might be hopeful that in some settings, we could get away with sort of quote unquote loose privacy guarantees, at least loose analytical privacy guarantees. That's a very catch. And here, each of these columns here corresponds to a different concrete adversary that in particular makes different assumptions about what the adversary can and cannot do. And so what this means is that here we have to be comfortable with making these assumptions before we can tolerate sort of this loose analytical guarantee. Because if the adversary is indeed as powerful as, for instance, this last adversary here, they could actually mount an attack that would extract as much information as the privacy analysis would tolerate. And so here, to give you an idea, the most concrete adversary on the left is only able to interact with the model as a black box, basically querying and observing predictions. And here, the adversary is able to do things like modifying gradients during learning, modifying the data set that the model is learning from, etc. And so while it is true that this might be an adversary that is difficult to instantiate in practice, ruling out this adversary does require making assumptions about what the adversary can and cannot do. Whereas because you can see this line is horizontal, this is one of the main benefits of differential privacy. The guarantee does not depend on what the adversary can do. So you can train your model with differential privacy, let it sit on a shelf, and no matter what people come up with in terms of new attacks, your guarantee is going to be holding in the future, regardless of what new discoveries are made. So this is basically to give you an overview of how to interpret the analytical guarantee and how to measure in practice how much concrete adversary could leak private information. This is very interesting in the sense that it draws a subtle connection to some research that we've done with many other researchers in the community on adversarial examples. So on adversarial examples, when we first discovered sort of that adversarial examples existed and then tried to defend against them, we realized that there's sort of an entire class of strategies that's not a valid defense strategy because it performs something known as gradient masking. So the idea is to say, well, if I try to make adversarial examples harder to find by manipulating the gradients of my model, this is in practice not giving me any concrete security because we know we can find adversarial examples in a black box way by transferring them from a different model whose gradients have not been manipulated. And so what that means is that while it is true that when you have models whose gradients have been masked, it is harder to find adversarial examples on that model specifically because the optimizers do not have stable gradients to learn from to find the perturbation. An adversary that is able to perform a black box attack actually performs much better and is able to evade these kinds of defenses. This is something we identified with black box attack. So this here should be contrasted with what happened in the differential privacy community, where the differential privacy guarantee actually holds no matter what adversaries will be able to do in the future. And I'm going to show you exactly what a concrete advantage of that strategy is. So in privacy preserving research, you can find results that suggest that because a lot of the privacy attacks rely on confidence information from models' predictions, hiding the confidence of a classifier might provide some privacy at a very cheap expense to the model owner because they don't need to do much, they just need to not reveal the confidence of their predictions. What we found in our work here is that this is actually not true because an adversary could adapt and find attack strategies that do not rely on the confidence. In particular, you could estimate the confidence of the model by repeatedly querying it on perturbed version of the input that you're trying to leak private information about, and then essentially reconstructing a proxy for the confidence through this repeated query. And what this graph is showing is that the accuracy of an attack that does not rely on confidence that we introduce here, the boundary distance attack, which is in the orange line. This attack performs equally well than the previous attacks that have been proposed that did rely on confidence. And so what that means is that having access to the confidence core does not tell us anything that we did not know already by being able to read the label, only the label that the model is predicting. So this means that the defense strategies that are trying to hide the confidence score are not giving any form of privacy. It's not meaningful for the end user. Instead, if we had trained the model with differential privacy, we can see here that this is where we achieve the best robustness to these attacks against privacy while still having a model that has good utility. And so this is remarkable because if you contrast this with what happened in adversarial examples, where we still don't know how to defend against adversarial examples, here there is a way to obtain provable privacy guarantees, and these hold against very sophisticated adversaries, even adversaries that are aware of the defense strategy. So this is a significant win here for differential privacy. So the next reason why differential privacy is not a silver bullet, though, is that it doesn't provide all flavors of privacy guarantees you might be interested in. And in particular, in the security community, there's a lot of work on cryptographic tools to provide confidentiality, where the guarantee here is not the same than different privacy, because you're trying to basically ensure that only people who are authorized to have access to the information have access to the information. But that doesn't mean you're trying to make inferences or statistical inferences about data set as a whole, or individual points in the data set as a whole. So here, this is where we have to use cryptography in conjunction with differential privacy to provide this different flavor of privacy protection. And in the following, I'll just refer to this as confidentiality to avoid any ambiguity with differential privacy. And so this is where, to answer Chengi's question from earlier, this is where we can extend, for instance, a framework like Pate, which provides differential privacy, with cryptographic primitives to obtain also confidentiality. And in particular, this allows us to implement Pate in a fully distributed setting, where in the previous work that we've done, we had assumed that one party was holding all of these teacher models and performing the training and then the noisy aggregation. Instead here, we're going to perform this aggregation in a distributed way. And so the best example of this is the network of hospitals that would like to collaborate and collectively predict on test inputs. And so each of the hospital has its own data set, has its own teacher model that they independently trained ahead of time. And now all they want to do is they want to be able to query other hospitals to get help on some of the test inputs that they're unable to classify with sufficient accuracy. And so this is illustrated here, and this is something we call capsi, confidential and private collaborative learning, where the querying hospital is going to submit a test input in an encrypted way. And then the other hospitals that are helping this first querying hospital to classify that input are going to use homomorphic machine learning to be able to infer on this encrypted input, which means that they all produce a label, which is going to be the basis for one of the votes in the Pate histogram. Then what happens is that we're going to use some two-party computation to essentially turn the prediction of each of these responding hospitals into a one-hot vector, which we can then sum to obtain the histogram that we obtained in Pate previously. We can then follow Pate, add noise, and then return to the querying party only the aggregated output, which is the noisy argmax, the label that received the most number of noisy votes. What this means is that the answering hospitals have differential privacy guarantees with respect to their training set, to their training data points. So they know that by participating in this collaborative protocol, they're not revealing private information contained in their patient's information, patient records. They also don't have to reveal their models to the querying party because they retain locally their own individual teacher models. And of course, the querying party did not have to reveal the test input because the test input was sent to the other hospitals encrypted. So we get these nice both confidentiality and differential privacy guarantees. And this works well even if the different teachers are trained by the different hospitals using different architectures, different model classes, etc. What we found in our evaluation is that this allows the querying hospital to improve the fairness of their predictions, because in practice, what happens is that if the different data sets are imbalanced, and this is again to answer Cheng Yu's question from earlier, and we don't have the same sort of benefits of having split the data uniformly as we had initially assumed at T. If instead we have some imbalance between different classes, then the querying party can essentially learn from the other hospitals by interacting with them through this capsi protocol, and then they can, of course, fine-tune their own local model using these labels, which will then improve, in particular, its accuracy, but also at times its fairness. And so this is a very interesting result where you can see that you can obtain both guarantee, but that you need different mechanisms. You need both the differentially private mechanism from the Pate voting mechanism, but also you need the cryptographic primitives to obtain confidentiality. And this is where I want to pause a second and compare this capsi protocol with federated learning, because federated learning does not provide privacy to the user, especially when you compare it to something like a collaborative framework like capsi. And the reason is that in federated learning, you instead assume that there is a central server. And so what the different clients are doing is they're helping the central server train one single model from their own individual data points. And so you'll notice that here, if we're simply asking individual clients to send back gradients to the central server to help train this joint model, first of all, you're not getting the same benefits here of having heterogeneous models across the different clients, because these clients are all receiving the same model and they're all participating in training the same model. So there's only one model to train, which means that everybody needs to agree on the same architecture, the same training algorithm. Second, this way of performing the training mostly provides confidentiality in the sense that rather than sending the data, you're sending now gradients to the central server. It does not provide privacy in the sense of differential privacy, because the gradients themselves contain the training bits. And this is why federated learning, the vanilla implementation of federated learning, is not privacy preserving. And you can see this in, so this is from the paper here at the bottom. This is a demonstration of how well you can reconstruct the training points from the gradients that are shared in federated learning. You can see here the original training points, and here what is reconstructed from the gradient. And the reason is that the gradient itself contains the data point exactly. So you don't need to do any optimization, any reconstruction attack. It's there exactly in the gradient. So all you have to use is essentially, in the case of an image data set, all you have to use is import matplotlib and plot the gradient, and you'll see the training points are in the gradients directly. And so what we need to do here is not only to train in this distributed way if we want to obtain confidentiality, but we also need to add a differentially private mechanism in order to also protect the privacy of the data that is contributing to the gradient computation. The problem is that because here we assume there is a central server that is aggregating all of these individual gradients, if the central server is malicious, then we find that there is no current good implementation and deployment strategy for federated learning that provides meaningful privacy guarantees for the end user. And if you're curious about why, I encourage you to read the paper here where we discuss this in more details. The one caveat of differential privacy, having said all of that I haven't covered yet, is a tension with fairness. And this happens even in more concerning ways when the distribution that we learn from has heavy tails. And this is very common in healthcare data, which is where we first investigated this tension, where we found that if one trains with differential privacy, then patients from the majority subpopulation have an influence that is greater than if we had not trained with privacy. And in particular, we find that the data records that correspond to patients from the majority subpopulation influence the incorrect predictions that we make about the minority subpopulation. And this is something you can see here in this graph, where without privacy, both majority and minority patients have influence as depicted on the vertical axis on the predictions, whereas here with high privacy, now most of the high influence points are from the majority subpopulation. So what this means is that there is a tension not only between accuracy and differential privacy, but also between differential privacy and fairness. And so why that is the case? Well, intuitively, what happens is that when you want to obtain fairness in a classifier, this usually requires high performance of the classifier on points for which we have very few examples of in the training set. Instead, when we learn with differential privacy, we say we should not learn from points that are rare and unique in the training set. And so you can see there's this tension where differential privacy prevents us from learning from the tails of the distribution, and fairness says we should care about the performance on the tails of the distribution. And so mitigating this trade-off is not trivial, and unfortunately may lead to some higher level societal decisions that we need to make, where we need to decide which property we may want to favor. Do we favor privacy? Do we favor fairness? Do we give up privacy for some abusers? These are very difficult challenges that we don't have good answers to, and I think they will be an important problem to solve if we want to be able to practically deploy privacy-preserving mechanisms that provide differential privacy in data sets, healthcare data sets, where fairness is, of course, very important. And then in the last few minutes, I'd like to give one last example of a property that differential privacy does not provide. And this property is motivated by changes in the legislation that favor mechanisms that allow users to delete their data, for instance, after having shared that data with a company. And so what we want to do there is we want to delete that data from the data set, but we also have to wonder, do we need to delete the data from the model? Because we know that if we've trained a model from a data set, there are risks that the not only the model is influenced by the points in the data set, but it may also have memorized some information from these points, which may then leak later on if we kept the model despite having deleted the point from the data set. And so this basically asks us to develop something that we can call machine unlearning, where we take a model that has already been trained, and we now say, how do we update this model so that we can unlearn one of its individual training points? And so here, you might think, well, let's just train the model with differential privacy, then we don't need to unlearn at all. And this is true to some extent, but not fully satisfying for the end user that deletes their data point. And the reason is that differential privacy bounds how much we've learned from each possible training example. There are two problems with that when it comes to machine unlearning. First of all, the guarantee is for each possible training example. Whereas in learning, we only care about one or a small number of examples that we want to unlearn. This means that we're basically not getting a guarantee for the right points, in the sense that it's an overkill to give this guarantee for all the possible points. Second is the problem that it bounds, differential privacy bounds. It does not make it zero. And so what that means is that if we want to unlearn, we would like that bound to be zero. We don't want the point to have influenced the model at all. And so of course, if we do this with differential privacy, we have to do this for all possible points in the training set. And so we cannot learn anything from the training set. Okay. And so machine unlearning is not as simple as, for instance, adding a gradient back after having completed training, because there is inherently a lot of stochasticity in the way we train machine learning models, in particular the way we train deep neural networks. And the fact that the training is incremental means that it's very difficult to, after the fact, estimate how an individual training point influence a particular model. And it's hard, of course, to reverse this influence. So to define what we would want to achieve when performing machine unlearning, what we eventually decided on as definition is to say, well, let's look at the distribution of models that we achieve at the end of training. And what we would want is that if we learn from a data set that contains a point, then unlearn a specific point, we should obtain a distribution of models that is identical to the distribution of models that we would have obtained if we had learned from the data set without that point in the first place. Okay, so this is what you see here, where we learn and unlearn, whereas here we just reinitialize and train again, but without the point that we want to unlearn. And we should obtain the same distribution of models in these two processes. And so, of course, a naive way to satisfy this definition is to say, well, once I have an unlearning request, I remove the point from my data set and I start training from scratch. The problem is that this is very expensive. So what we propose here is to introduce two changes in the stochastic gradient to make it easier to then perform this retraining operation, in the sense of it will take less compute effort. And so here, this is how we illustrate this process, where if you recall in Pate, we had this partitioning mechanism where we split the data set in multiple subsets of data. Here, we're going to do the same thing again, because if we partition data, then train a lot of smaller models on these partitions, then when someone would like to unlearn a point, we only need to retrain one of the models in the ensemble, the model that contained the point in its partition of training data. So that already makes it a little less expensive to retrain, because rather than retrain a big model on the entire data set, we now have to retrain only a smaller model on less data. Then we introduce a second knob, which amplifies benefits of doing this even further. And that second knob is to say, well, rather than go through the entire training set during each epoch of training, let's gradually introduce the training data to the algorithm. And so what we do is we further split each partition in multiple slices. So we now have here these multiple slices. And we start by training on one slice. So it could be, for instance, 10% of the shard partition here that I had initially. And I train on these 10% data points. I then, after a few steps, I save the checkpoint. I save the state of the model. And then I introduce an additional slice of data, and I continue training, and then save again the state of the model in another checkpoint. So you can see is happening here is that I save regularly the state of the model before I introduce more data points in the training set. And what this means is if someone asks me to unlearn, I can locate the slice in which their data was contained, revert the model back to the last state that was known before introducing that slice, and then resume training from there. And in expectation, this will save me time because I won't have to restart training from a random initialization for most points. Okay, and if we combine these two together, then we get essentially improvements in how quickly we can handle the requests by retraining only the relevant steps and the relevant models in this ensemble. Okay, and so this is essentially just an overview of the approach. I encourage you, if you're curious about learning, to check out my website. We've recently published a few results on unlearning, showing that it's in particular very difficult to provide unlearning guarantee that the user can audit themselves and from their inspection of the model that is released, for instance, by a company, decide whether or not the company really has audited their point. And again, this is work that is available on my website. So with that, I will conclude. I will say before I take questions that I think at a high level, differential privacy is an excellent definition. And when it is used properly and in the context that the definition has been created for, it does provide an excellent framework to reason about privacy in machine learning. And I'm in particular very excited about the side benefits of using differential privacy, such as the fact that a differentially private model generalizes very well. You can, for instance, see that the training and test curves are nearly identical when you train with differential privacy. And so I think this is something that in general is true for trustworthy ML research, is that it allows us to tackle very fundamental problems that the machine learning community is trying to solve. I think that's very exciting as security researchers. With that, I'll conclude here, and I'll thank in particular our sponsors, but also all of the students that contributed to this work. And I've highlighted here that Adam and Marlene are both on the job market this year. So if you're recruiting, feel free to reach out to me if you need an introduction. Thank you, everybody, for your attention.
Thank you. Now